Yesterday we looked at salts. I gave you a set of questions, well, 1 page, 2 sides, homework I wanted you to take a look at. Here are the answers to them. The front page looks like this. You're identifying acids, bases, and salts. So I had some students who, they were like, I have a secret way of doing this. And their secret way of doing this was, if the formula had an H at the front, it was an acid. If the formula had an OH at the back, it was a base. If the formula had neither, it's a salt. That's not the secret way. That is the way. There's nothing secret about this. That is the way. So there they are. Acid, acid, base, acid, base, acid, acid, acid. Salt, base, base, salt, acid, salt, salt, salt. Acid, acid, base, acid, base, salt. Comments, questions, concerns on that page. I heard some of you explaining things to your peers. That is great. Always, this is a positive thing. And then questions 2 through 7. What acid is present? What is the chemical name for yada, yada, all those things? That would have come from, most of those would have come from the table I gave you, or the 2 tables that I gave you on the day I introduced to you acids and bases. So you've had to have gone back and look at that. The acid in vinegar is acetic or ethanoic. Both names are valid. We talked about how table salt is sodium chloride. Car batteries is sulfuric acid. The base found in Drano and oven cleaners is sodium hydroxide, or NaOH. The base active ingredient in some antacids, you could have either said milk of magnesia or MgOH2. And then the acid produced in the stomach is hydrochloric or HCl. However you want to give me that answer, is the formula or the name is fine. So that was the first page. The second page is where things got more interesting, because you actually had to finish the formulas and then balance them. So this is the top part of that page. I balanced all of them because I was on a roll and wasn't really paying attention. But I only wanted you guys to actually go ahead and balance A, C, E, and G. But for those who did more, I did all of them. They weren't overly difficult ones to balance, I didn't think. But still a good way to go back and review how you go about balancing. If you got something different than I got, don't assume that you, oops. Comments, questions, concerns on any of that? And for those who were away yesterday, I am aware I did not get the videos posted. I had to leave early yesterday, so they didn't go up at the end of the day. They will today. But yesterday's lesson was pretty short. You'll be okay. Comments, questions, concerns. Kaylee, did I make any mistakes? Nope. You're always the one that either finds them or says them, so. Okay. Then I'll give you the things I did on the bottom. Here they are. I didn't want you to have to balance these. Even that, that would be a lot of work. So I did tell you didn't have to do that. I just wanted you to complete the word equation and the formula equations. So this is my completed formula, like the products on the formula side. I didn't bother going back and doing these. I could have, I suppose. I didn't. I could fill them in right now, I guess. This would be HCH3COO plus BaOH2. This one would have been H3PO4 plus AlOH3. D would have been HNO3 plus LiOH. This would have been H2SO4 plus CaOH2. And F would have been HCl plus MgOH2. Okay. Comments, questions, concerns on any of those? The way I recommended you do them for those, so for the few who were away yesterday, the way I recommended you handle these This is what would have been given to you. This was all blank. So I recommended you do this to this to this, and then go back and finish the naming portion, like the word equation portion, by naming what products showed up here. Is how I would recommend you do a question like this. From here, to here, to here, and then up to here. Is there anyone who wants me to go through any of those kinds of questions? Comments, questions, concerns, queries, conundrums, or consternations? Which are all really the same thing. I just pull out a thesaurus. There's lots of whispering in the back. Are we good back there? Brooklands? Okay. Okay, so then if there aren't any questions, or even the balancing, we were good with what happened up here. Some of the ones you needed to be careful with when building these products, but again, we're looking at charges. It's all the same stuff that we've done. Hearing no questions, I mean, should fill me with great confidence in your abilities, but it's kind of scary when there are no questions. Okay, cool. Then if there are no questions, that's acid-base neutralization reactions. They don't get any more complicated than that. The only thing I could do is swap out what kinds of acids I give you. The bases aren't overly difficult. Like these are the kind of the grossest ones I could give you. Things with like iron and tin. The multivalent bases are really the worst kind that I could give you. So if you're comfortable saying, yeah, an acid and a base is always going to give me water, and then I can build the salt, then you're going to be good. Where things are going to get interesting today, flip the page to here, is I'm now going to give you 5 more reaction types, and you're going to have to identify what the reaction is and then remember the kinds of products that pop out. So here we go. Let's do it. So, one of the most important skills to develop in science in general, not just chemistry, but in every science you could possibly take, is the ability to identify information and make predictions. That's like, I mean, that's just kind of life, though. Identifying what's important and then making predictions of what's going to happen based on what you've seen is a skill you need to be able to do everywhere. It just doesn't get broken down quite as directly as we're going to break it down today. So in chemistry, chemists must be able to identify what is present. So like we did it yesterday. This is an acid, this is a base. Cool. When an acid and a base react, I know we're going to get a water and salt. Or when this reacts and this reacts, I know this is what's going to pop out. So especially if you find yourself on the cutting edge of chemistry, like you decide that chemistry is what you want to do as a profession, whether that looks like going into pharmacy or going into like a full-on doctorate in chemistry and working for a gas company or whatever. If chemistry is in your future, this is an important skill to be able to have. There are 6 main reaction types that we're going to look at. These are the most common reaction types, and even then, I have yet to see a chemical reaction that can't be broken down into one or a couple of these that are kind of happening simultaneously. So these are the most important 6 types of reactions that we're going to look at, and here they are named for you already. Synthesis, decomposition, a single replacement, a double replacement, an acid-base neutralization. This we've done already. This was yesterday. And a combustion, which you might think you're familiar with, but what you're probably familiar with when we talk about a combustion is a very narrow type of combustion, and there are more. So before we even get into this, I want to talk about what these words are and what they could mean based on what you know already. So, if I say the word synthesis, what comes to mind? What do you think of? Other things that have similar names. Sorry? Photosynthesis, okay. In photosynthesis, what happens? Why is it called photosynthesis? Someone really quickly explain photosynthesis to the class. Every one of you who I taught Science 9 to who isn't volunteering this, shame on all of you. Sunlight does something. Okay, let's talk about photosynthesis. Photosynthesis is done by plants. It takes in light. They take in carbon dioxide, and what do they do with the light and carbon dioxide? And water. They take in CO2, they take in H2O, they take in light, and they produce something. Come on. Oxygen is one product. They produce oxygen. That's why we have oxygen to breathe on this planet. They also produce, starts with a C. You eat these things. Sorry, louder. Say who said that? Bob Kirk, say it louder. You're sure it's not the answer? Okay. That is not the answer. You are correct. That is not the answer. Carbohydrates, carbs. They produce carbs. They produce oxygen. Two things that you need, which is why we eat vegetables, among other reasons. So the reason it's called photosynthesis is because light is required to make something new. So synthesis takes in some things and creates something new. And you might think, well, don't all reactions just create something new? Yeah, but not like this. Synthesis or a synthesizer. What's a synthesizer? Do we know what this is? It's an instrument. Are we aware of the instrument called a synthesizer? A synthesizer is an electronic piano. You can program all sorts of different sounds to make new sounds. Synthesize means you're creating a new thing. A being an important word there in that sentence. One new thing. What does it mean to decompose? When I use that word, say that word decomposition, what do you think of? Dirt? Why do you think of dirt? Because you compost, and then as you throw the things into the compost, it does what? Don't use the word decompose to define the word decompose. Two words, B and a D. Breaks down. So decomposition is the process of breaking down complex molecules into smaller, simpler bits. You had a head of lettuce that rotted in your fridge. You put it in the compost. Now you have dirt. It rots. It breaks down. If it rots in your fridge, that's why you get that pool of disgusting looking green water at the bottom of your veggie drawer. If you've never seen that, it either means you're not buying lettuce or you're actually eating what you buy, which is better. So decomposition is the breaking down. And I'm going to go through specific examples of all these things, but the words, the names, should trigger English concepts you're already familiar with. Single replacement. What does the name suggest is happening? You're replacing one thing. I mean, the name there is fairly straightforward. Double replacement, what's probably going to happen here? Two things. Double means two. Replacement is, well, something is getting swapped out. I'll put a note down here for the single replacement, and we'll talk about it again. The meme just has so much life. This is your distracted boyfriend meme. There is so much use I get out of that meme every year in science. Acid-base neutralization, we talked about it already. You have an acid, you have a base. You can identify that, you're golden. Combustion is more interesting. When you think of combustion, what do you think of? Sorry? Together and something goes boom. So typically we think of explosions. And the most interesting combustions are, like it's how we power a car. You let the gasoline go in, you mix it with the oxygen, you spark it, it explodes, it pushes a piston, which pushes another piston in, which causes an explosion. And you get this. That's how a internal combustion engine works. An explosion pushes a piston, which pushes another piston down, which makes an explosion, which pushes the piston back, and the pistons are going like this, back and forth, repeatedly, every time something explodes inside your engine. It's a controlled explosion. But not all combustions are this way, and so this is the one that we're going to need to make note of. I'm going to show you what might be the slowest combustion you will ever see in the lab. Or we do it here. I might do it here. We'll see. Okay, so these are the reaction types, and the names are going to give you an idea of what's happening here. The combustion explosions, let's finish this one up here, always involve what? When you think of a combustion, what are the kinds of things that are combusting? A combustion is a very specific kind of explosion. Not everything that explodes is a combustion. Where do combustions happen? Brooklyn. So it's oxygen plus what other kinds of things? It's going to make fire. But again, not all burning is a combustion either. No, heat and fire is the same thing. What's going right here? Where do we think about combustion? I gave you one. I talked about gasoline in a car. Not just gasoline, though. What other kinds of fuel do we use in a car to make a combustion engine work? Starts with a D. Diesel. Sometimes combustion reactions happen on your patio or your deck outside your home. And we use them to make steak if you eat meat. Or maybe you want to roast vegetables if you're a vegetarian. Propane. Barbecue. These are all from the same family of chemical. Does anyone know what the family of chemical is that contains gasoline, diesel, and propane, among other things? Okay, well then we'll come back to that. Okay, let's talk about these reactions now in more detail. I'll go through all of them. The first, and we're going to go in order: synthesis, decomposition, single, double, acid, base, and combustion. Here we go. So the first one is synthesis. And the name is what's happening here. In a synthesis reaction, single elements combine.
Thank you.
Have a good time at the pool there, Mahib. To produce a compound. It's the simplest kind of reaction I could ever give you. Two single elements react to form a compound. And so the general example I'm going to give you is something like this. Let's say I have element A and I have element B. These guys are going to react, and they're going to produce a compound. Let's call that compound AB. Don't know what it is, but this is the general form of things that happen. One element plus one element gives you one compound. And so I've got two examples of it down here. Magnesium metal reacts with oxygen gas to form magnesium oxide. Magnesium metal is an element. It's just Mg. What's the formula for oxygen gas? O2. Oxygen is diatomic. On its own, it's going to be O2. This is still a single element and a single element. When these guys react, what are they going to make? What's the charge on magnesium? What's the charge on oxygen? It's just going to be magnesium is +2, oxygen is -2. It's just going to be MgO. We'd make it the same way we made things before. That's +2, that's -2. You swap and drop and reduce. You're going to get MgO. Now we could go ahead and balance this thing. Let's balance it. Why not? Because the 2 here is going to mess people up. To balance this thing, I need to balance the oxygens. What could I do over here to balance this reaction? Toss a 2 out front. And then when I do that, how do I go back and balance the magnesiums? I put a 2 in the front of the first magnesium. And now this is a balanced synthesis reaction. When you make the product, you have to use the charges. And then we can go back and balance the thing. Okay, next one. Nitrogen gas can react with oxygen gas to form something called dinitrogen monoxide. You might also know this as nitrous oxide. You might know it as just nitrous. If you are familiar with a particular movie series, where have we heard of nitrous? Sometimes it's referred to as NOS. What movie series am I thinking of? The Fast and Furious. NOS is a gas used in cars to give them a boost. It's also used at the dentist office. If you need a pain, and while delivering children, I've discovered. Because that same thing that helps you get a boost out of your car also is used to give you a mild high. It's used for either dental procedures or women giving birth. It's called laughing gas, is where you might hear it as, and it makes you euphoric. It doesn't numb the pain, you just don't care about the pain anymore. So, this is nitrous oxide. Nitrogen gas, the formula is N2. We're going to react it with oxygen gas, which you've already seen is O2. This one I have to give you the name for. These are both nonmetals. They are both negatively charged. We need to be specific in how these things do combine. We're going to look at dinitrogen monoxide. What's the formula for dinitrogen monoxide? The di on the nitrogen tells you what? There's 2 of them. So it's going to be N2. And then monoxide is just going to be N2O. Yeah. That's laughing gas, or NOS, depending on the situation you're in. Same compound, used both ways. Comments, questions, concerns. Synthesis reactions are really straightforward. 2 individual elements, 1 compound. When you're ready, flip the page. I want you to do those 5 right now. Crank them out. Those are all synthesis reactions. What are the products from those reactions? Regina, if you can avoid it, now's not a great time. unless it's a legit emergency. Go fast. Go fast. Yep. Okay. Dragon, one, go. Okay. Which part? Okay. Okay, like the building of the combat? Okay. So we build them just like it's a little different. The formatting is different than what we did at the beginning of the unit, but otherwise it's the same. If I said, if I gave you this like a month ago, if I said you have magnesium and you have nitrogen, and I want you to build the compound with you. How? You swap and drop, so we need charges. Magnesium has a charge of +2. Nitrogen has a charge of almost -3. So swap and drop. Mg3 and 2. So the product that forms with magnesium and nitrogen. The only thing I'm doing is just saying, okay, well, let's change it. Instead of just giving you Mg10, I'm just writing it like this. So it means the exact same thing. Same procedure. The only thing that changes then, so like we have Mg plus M2. This is actually how magnesium and nitrogen is. This is what we did before. Is what make for me magnesium nitride. Do this. +2, nitrogen has a charge -2. At that stage, when I gave you the name and asked you for the formula, nobody asked, well, how does this happen? Now we're looking at how it happens. If I took magnesium metal and nitrogen gas and I forced them together, this is how they would react. But then to build the product, we're just going to say, well, Mg has a charge of +2. Nitrogen has a charge of -3. So when I get the compound, it's going to be Mg3 and 2. And now we can go ahead and balance this. Does that help? Oh, some days it's full and some days there's nobody. We good? Okay. What are we doing over here? Okay. Finish. Is tired too. You don't have to do any balancing. I just want you to build the products. Okay. So, Romina, what's A? Mg3N2. Yes. Eeny, miny, I don't know. Muller. B. What's the product? You sure? Matthew disagrees with you. Matthew, why do you disagree with Muller? It's gonna be. It's gonna be. Why? So the charge on aluminum, Al is +3, F is -1. So when you actually build the thing, it's going to be AlF3. This 2 is only here because fluorine on its own is diatomic. You have to build it properly, invoking the charges. You have to always swap and drop, and then we'd go back and balance the thing. We'd say, okay, well, I'm going to toss a 2 there, a 3 there, and a 2 there, and now it's balanced. You build this thing using the charges. It doesn't matter that this is F2. You care about the individual charges on the aluminums and the fluorines, and then you can go back and balance. I told you didn't have to, but I'm going over why we don't care that subscript is there when you're building the thing. Okay, C is K2O. D is CDI2. And E is CS3P. Yes. Because the charge on phosphorus is -3, and the charge on cesium is +1. Cool. Comments, questions, concerns on any of those? Those are all synthesis reactions. Individual elements, single compound product. Okay. Hearing nothing, let's move on. The second type of reaction named was a decomposition. And a decomposition reaction is exactly what you'd expect from the word decomposition. You take something complicated and you break it down into its individual parts. So the simplest kind of decomposition looks like this. You said, I'll give you the definition first. A compound breaks down into individual pieces. And the compound can be anything. It can be a big, ugly carbohydrate, or it could be something relatively simple. The simplest version I can give you of this, let's say the compound has the formula AB. There's our compound. Generally, when we decompose something, something is doing the work. You might have to add heat. In the case of decomposition in your garden or in your compost pail, you need some form of bacteria is present doing the work. But generally, as a chemical formula, you're going to start with a compound AB, and it's going to get broken up into its individual pieces. A plus B. The mechanism that does the breaking changes. Sometimes you need to run electricity through something. Sometimes you just need to heat it up. Sometimes you need to bring in a catalyst or some bacteria or something to do the breaking. But that's a decomposition reaction. So I got two examples for you. The decomposition of table salt by electrolysis. So electrolysis is a procedure where you run an electric current through a compound. You might have a crystal salt, and then you electrify it. When you do that, you produce sodium metal. So sodium on its own as a pure element, and chlorine gas, which is wildly toxic. So you get something like this. NaCl breaks down to produce Na and Cl2. You just break it up into its individual parts. The important parts to remember here, the diatomics and the polyatomics are going to get produced as diatomic elements or polyatomic elements. So if you recall, the ones you want to be aware of are things like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are the diatomics. They form the number 7 up in the top right-hand corner. And phosphorus and sulfur are also polyatomic, P4 and S8. But a decomposition doesn't have to break a compound into individual atoms. It could break a compound into a bigger compound into subcompounds like this. So like you take your pop, whatever it is, the pop you are drinking, you crack the lid or you break the seal on the can. As soon as you do that, the carbonic acid that's in there, the H2CO3, breaks down into water and carbon dioxide, CO2 and H2O, which is why your pop gets flat. This added water here makes the pop flat. And the CO2 is the bubbles. This is also an example of a decomposition. Even though it's not individual elements being produced, these are simpler molecules than what you started with. Comments, questions, concerns about the decomposition. And I'm going to do demos for all of these things tomorrow. Most of them will be in here. One of them has to be outside because it's awesome. Okay. Flip the page. I want you to decompose those 5 things. Decompositions should be easier than synthesizing. On your mark, it's a go. Decompose them. Sorry? Thank you very much. I will fill that out and hand it in. Boom. Okay, those should all be done. What'd you get? They really are that straightforward. Anybody, what do we get for letter A? Or do I have to start calling names again? Who have I not picked on yet? Sahej, what'd you get for A? You're still doing A. Matthew, what'd you get for A? You're still on the first one? Okay. Olivia, what'd you get for A? AU and, sorry? Cl2, sweet. Chlorine's one of the diatomics. Gold chloride is going to break down to gold and chlorine gas, you betcha. B, what are you going to get? K plus O2, you bet. C is going to be Mg plus F2. D is going to be, I heard it over here. Sarah, was that you? Did you say the answer to this one? Oh, okay. Is it Kaylee? I thought I heard a voice from the middle table. Sarah, what am I going to get? You can do it. Yeah. Plus? Almost. N2. Nitrogen is one of the diatomics. That's really, with the decompositions, that's the really big thing to watch out for, is am I producing something that's diatomic? Otherwise, the decomposition really is just this straightforward. What's E going to be? CS plus I2. Decompositions usually produce diatomics, but not always. Yes, Brooklyn. Can I explain D? Sure. Okay. What part of D is messing you up? Okay. So the easiest way to do this is by drawing it out. So Ca3N2 is going to look like this. I've got, how do I want to do this? I've got an N and I've got an N, and these guys look like this. I'm going to do Lewis diagrams for all these things. Ca has, yeah. Okay, so there's my Lewis diagrams for the making of this guy. I've got Ca3 and I've got N2. So when I make this compound, if you recall, these calciums are all going to donate electrons to these different nitrogens. So that when they, and when that happens, you're going to get Ca, that's going to be +2, and there's going to be a nitrogen there, and then there's going to be a Ca there, and there's going to be probably another N there, and then another Ca over here. So you're going to get a crystal that looks like this, alternating calciums and nitrogens. This is what Ca3N2 is going to look like. When you decompose this, when you electrolyze this, what you're doing is you're breaking the ionic bond between the calciums and the nitrogens by giving, effectively, you're giving the calciums back their electrons. And so what's going to happen is these calciums are just going to get spat out. And now the nitrogens are going to be hanging out like this. And because the calciums are totally content with the electrons they've now been given, and the nitrogens are pissed that they no longer have those electrons, the nitrogens are going to group together, and these guys are going to create N2. That's why this is why the diatomics are the way they are. Now, when we have these guys over here, because they have 2 electrons, they don't want to get more electrons, they're not going to group together. So we just lump them all together. They're just going to pile up like dodgeballs in a bucket. They're not interacting with each other, they're just there. And so the calciums are all going to just kind of clump together, and we don't call them Ca2 or Ca3 or Ca4 depending on how many are there. We just call it Ca. So it doesn't matter that there are 3 here listed as part of the name, the Ca3N2. When you break it apart, we just take all the calciums and we name them Ca. And we take all of the nitrogens, because the nitrogen has to bond with something, because it's a negative ion. It wants to bond with something else. So it will bond with itself. And then to satisfy the fact that there was 3 there, we would balance this reaction by putting a 3 out front. That's my really long way to explain that. Does that make sense? Okay. Brooklyn. Yeah. They don't have the same charges. Oh, they totally do. We made a mistake on this one. No, we didn't. No, you're right. They do have the same charges. That's why it starts as CS and I. When you take, and again, I'll draw this one out for you too. Sure, I can do that. There's my CS, there's my I. Iodine has 7 in its outer shell. It wants 1 more. So this guy's going to donate. So you're going to get cesium and iodine. But when you run electricity, when you electrolyze this compound, you're going to break all of these bonds, like the ionic bond that's there. Effectively, you're going to give cesium back its electron. And cesium is totally content to hang out on its own. In fact, all the cesiums are going to kind of hang out on their own. But the iodines are antsy. They have to have something to satisfy this. And so the iodines are then going to group up and bond with another iodine. But the cesiums don't need to do that. So the iodines are going to do this. The cesiums are just going to hang out. Bound together, yes. Where the cesiums, yeah, there's actually going to balance this, we'd have to put a 2 there and a 2 there. But the cesiums aren't bound together, so we don't put a subscript here. But we have to put the subscript here, and we don't have to put any subscripts over here, because the CSIs the cesium iodides aren't going to bind with other cesium iodides either. Does that help? Sort of? Okay. So we've got the synthesis and the decomposition. Perhaps you've noticed those are exactly the opposite of each other. Let's do the next one. Single replacement reactions. I'm not going to use purple because that's hard to see. Let's use pink. Okay, so a single replacement reaction looks like this. An atom reacts with a compound and replaces one of the elements. It's exactly the way you think. It's a single replacement. One thing gets booted out. This is exactly the distracted boyfriend/girlfriend me. So let's take a look at what that would be. If I have a single element, let's call that single element A, it's going to react with a compound. The simplest compound I could write down is B, but B is not a compound because there's only one of things. So to make a compound, I'm probably going to have to write down, what's the next letter in the alphabet? C. I've got element A is reacting with compound BC. It's going to replace one of those elements. How do we know which element it's going to replace? But which one's distracted is the question. Why C? Okay. Okay. I think you're on the way. Let's take a look at, if you recall, way back, Science 9, we reviewed it again at the beginning of this semester. When I write something like this, a compound gets written, what element always comes first? You're good, man. When you're given a formula for a compound, which one always gets listed first? The metal, and the metal is always charged positively. Thank you. So if you recall, when you list a compound, a chemical compound, the positive one always gets, ion always gets listed first. The negative one always gets listed second. So, but there is no restriction on this guy here. This guy, A, could be either positively charged, it could be a metal, or this element could be a nonmetal, it could be negatively charged. So depending on the charge of A, it's going to change which one of these guys gets replaced. So there's actually two options here to see how the chemical reaction is going to go. If A is positive, if it's A plus, what is A going to replace in this compound? If it replaced C, you'd have two positives together. It's going to replace B. So if A is positive, B is getting replaced. You're going to get AC plus B. The same sign is going to change places. If A is negative, what's going to get swapped out? C is going to get swapped out. So you're going to get BA plus C. You were going to ask why it's not AB? But you figured it out. Because which one always gets listed first? Positive ion. Good. So, an example of this. You are actually going to do this reaction in the lab for me on Friday. I've got the lab booked for Friday. You're going to do this reaction. You're going to take aluminum foil. You're going to place it in a solution of copper 2 chloride. You may have done this one already for me in grade 9. I don't remember. But you're going to do it. What's going to happen? Let's take a look. Aluminum is just what? What's the formula for aluminum? Al. It's going to react with copper 2 chloride. What is the chemical formula for copper 2 chloride? It's going to be CuCl2. Because copper 2 is Cu with a charge of +2, chlorine has a charge of -1, you swap and drop, and now we've got CuCl2. So there's my aluminum. It's going to react with a solution of copper 2 chloride. What's going to happen? What is going to swap? The Al and the Cu. This guy's positive, this guy's positive, so these are the two that are going to swap spots. The Cu is going to come out of the compound, and then what's the chemical that we're going to get, or the compound that we're going to get as a result? Almost. Almost. How do you build a compound out of aluminum and chlorine? Nope, it's not Al. You have to swap and drop. So then what's the charge on aluminum? It's 3. The charge on chlorine, you're going to get Al plus 3 is going to react with Cl minus 1. So what should the compound that is made up of aluminum and chlorine be? AlCl3. Swap and drop. Things are getting more complicated. Flip the page. I have 5. I want you to do them all. On your mark, get set, go. I want to get you to help me with a bunch of these reactions tomorrow. Yeah. I want you to do those 5 for me. It's getting more interesting because we're actually getting closer to actually doing chemistry. You're swapping out whatever is the same charge as the same. So the first one. So aluminum is going to be positive, so what's your first swap? PB. The second one, Na is positive, so it's going to swap with. Yep. The third one, magnesium is positive, so it's going to swap with B. Fourth one, Cl is swap with. Good. Last one, B is positive. So now that you've identified that, you just have to go back and finding the specific charges. This guy's positive. This guy's positive. Those are the two switch spots. Switch. You replace one with the other. So the Al is going to boot out the PB. The PB is going to be alone. And the Al is going to go with the Cl. It's not finished. So now you've got, so you're right, the AL is positive, the ED is positive, so if these two swap spots are now alone, and the AL is chlorine, now you have to put this in front of them. The charge on aluminum is zero, plus 2 is the charge on chlorine. And move on. So then if this guy's plus 2, that guy's minus 1, now it's in one compound.
You gotta go literally for everything.
Good luck, win. We might get through one more reaction type. So, if you have aluminum, with a charge of plus 3, and you have chlorine with a charge of minus 1, how do you build that compound? So it's either me.
Want to go to PE.
Here, we wouldn't write this charge. The charge is listed here. Because aluminum on its own is in the new charge. This is something like that. You only care about the charges when you're trying to put them together, yeah? I did. Late, I forgot to change it. Careful with these guys. What's the charge on aluminum? Or what is the charge on aluminum? Right. So what should that be? Not CL4, it should be CL3. Okay, let's go fix.
Of course.
Okay, how are we doing? Are we done? These 5? Kind of, sort of. Okay, I see some pencils still going. First one. Aluminum is positive, so what's it going to swap with? The PB. So the PB is going to come out, and the aluminum is going to replace it next to the Cl, and now we need to build this compound properly. The charge on aluminum is? So then how many chlorines am I going to need? 3. Because chlorine's got a charge of -1, aluminum's got a charge of +3, so it's going to be AlCl3. The next one, Na is going to replace the Cu. So the Cu is going to come out on its own, and the Na is going to get together with the O. How do I build this thing properly? The sodium's got a charge of +1, oxygen's got a charge of -2. It's going to be Na2O. In C, Mg is going to swap with the Cu. So the Cu is going to go out again on its own, and we're going to get Mg with a charge of +2 is going to react with fluorine, charge of -1. So it's going to be MgF2. In letter D, the chlorine is going to swap with the Br, the bromine, because chlorine is negative, bromine's negative. So the bromine is going to go out on its own, and it's going to be CsCl, because cesium is +1, chlorine's -1. What do I have to fix yet in this thing? This is not a correct statement. Yes, Brooke.
Oh.
I was just confused because I thought that the single was the BR, I really thought it was after the
It doesn't matter.
We can do it either?
If you wrote, like, you mean you wrote it as CsCl plus Br?
Yeah.
It doesn't matter.
Oh, why?
What's the mistake, or what have I not finished? Nope. Sorry? It's got to be Br2. Bromine is one of the 7 diatomics.
Oh.
You always, sorry? Correct. Yeah, it's the negative ones. Those 7 diatomics, on their own, they will bond to another one of themselves. Metals won't do that, but those diatomics will. And then letter E, the beryllium is going to swap with the iron. So the iron is going to go off on its own, Fe plus, and now we need to build this thing properly. The charge on NO3 is -1, I believe, and Be has a charge of +2. So to build it properly, what do we need to do? Be, NO3's got to be in brackets, we can put a 2 outside. Very good. Cool. Shall we do one more? Yeah, let's do one more. Okay, single replacement. Done. We've done synthesis, decomposition. Those were opposites. Single replacement, and now the next one on that list was the double replacement. That pen kind of sucks, so let's grab gray. The double replacement reactions. They are going to be very similar to the single replacement, except the only teensy difference is a compound reacts with a compound. So if I'm going to give a generalized version of this, it would be compound AB is going to react with compound CD. These are almost easier than the single replacement, because when the replacing happens, there's no guessing what replaces what. What's the only thing that can happen here? What's switching? Sorry? So the A is going to swap with the C. So you're going to get CB plus AD. Just what was a positive and a negative and a positive and a negative, they just rearrange themselves. I mean, there are relationship examples I could give here, but they all kind of start to get dicey at this stage. So, compound reacts with a compound, and effectively the same signs swap spots. So an example of this would be this: a solution of potassium iodide and a solution of lead 2 nitrate will react when mixed. I think I've actually had you do this one already. You, in the iron chemist lab, I think you did this one. The lead 2, that's the positive ion in the lead 2 nitrate, and the potassium, the positive ion in the potassium iodide, are going to swap spots. So the Ki and the K and the PB swap spots. The PB goes with the I, the K goes with the NO3, and you get PbI2 and KNO3. You have to build, these things always get built with the correct charges, like K has a charge of +1, iodine's got a charge of -1, lead here has a charge of +2, because that's the Roman numeral listed, and nitrate has a charge of -1 when it's on its own. So when these guys swap spots, well, you're going to need 2 iodines to balance out the charge of +2 on the lead. And because this guy's got a charge of +1, this guy's got a charge of -1, you just need one of each, just KNO3. Positive charges can only change places with positive ions, negatives with negatives, because the reaction, just like the previous one, still involves charge balancing. BALANCING, charge balancing. So it's very similar to what you just did with the single replacement. It's just now slightly more work because you have to do it with both new compounds. So, last thing I'm going to ask you to do today, those 5 right there. And we will pick up here tomorrow. That is what little bit you have left there is your homework. You've got 6 minutes to do it. You could probably get it done. Take a look at those 5, and we'll do the last 2 types tomorrow. And then I've got demos for all this stuff. It'll be great. Your final version, when you get things down at the end, you can use them to help you build, but make sure you get rid of them. And you have to do the charge properly. What's the charge on the CA? What's the charge on OH? Yeah, so that's +2 and that's -1. You always got to make sure you're building them properly. If you've got CA and OH, CA is +2, OH is -1. And you have to do it for every compound. Metals always come first, and you got to balance the charges when you're building these compounds. With everything we've done, we're just putting all the details together. If you finish those 5, you can pack up. Otherwise, you shouldn't be packed up unless you're done. I will give you advance notice to pack up before the bell if you're just not there. Finish all 5? C is positive. N is positive. It's 2 swap spots. C is OH. Swap spots. Calcium is 2, OH is 1. Got to balance the charge properly. Okay, if you want to back up now, you can. Bell goes in 45 seconds. As much as they've ever fixed the bells. They got reset back to the appropriate time, and then in a couple weeks they'll be off again. But when we came back on Monday, they were correct. Right now they're bang on. We'll see how long that lasts. How good is today, as you said? Hey. Need a knife. I had a knife. Where did it go?
Knife shit. Get out of here. Oh shit, I just stole your chair. They're gonna like pull my chair. Oh, my God.
Nice. Pens are trash. Nice. I know.
Everybody like, don't throw. And then you just gotta wait. I was 10 seconds after. And so I was like, throw it. And then you're like,
Brand new class.
oh, no. You don't know. Okay.